Once again, welcome. Thank you for coming to this basics training for the OLI corrosion the OLI Studio corrosion analyzer. And I will be your instructor today. And I always like to start with this slide here because I will be using the latest version of the software, the OLI Studio Corrosion Analyzer version 11.5. So if you have access to any other software that is has a version below this number 11.5, you may obtain different or slightly different results, not completely different, but slightly different, because in every release we make improvements to the model, to the models, to some interactions, etc. So that slightly changes the results. So that's why you will see different numbers if you have a different version. I also, if you are using the MSCS RK, I recommend that you make sure that you have the 9.6 version and above to have access to that framework, thermodynamic framework. And we will be, like we were just talking about a moment ago, we will be recording this session so you have it for your future reference, and also you can share within your own team, and also you will be able to come back and see how we did certain calculations with the software, well, with the course. Oh, I forgot to introduce myself. My name is Diana Miller, and I am an application engineer at OLI Systems. I have been with the company for the past 5 years, and we have created this course with the help of my colleagues in order to try to highlight all the features that we have, to expose them, to show the clients all the possibilities, everything, all the calculations that you can do. And my background is chemical engineering and corrosion engineering. So I did a PhD in corrosion engineering here in the US in the University of Akron. And I have been doing simulation since I have graduated, helping clients around the world that come to us and ask us how to solve their corrosion problems that they see either in the oil and gas, now geothermal, also in metals and mining, different type of industries where they are seeing corrosion issues. So I have gained quite a lot of experience, at least from the simulation side, trying to understand when a corrosion phenomena is happening and how you can mitigate it or avoid it to reduce the corrosion issues. Okay, so with that, I'm going to turn off my camera. I don't know how I do this here in okay, here. And we can get started. So the course objectives. So the idea is that whenever we are working with the corrosion analyzer, think of the corrosion analyzer more like an add-on for the stream analyzer. The stream analyzer is the umbrella or the main interface that you will see when interacting with OLI Studio. You cannot do any corrosion calculations if you don't have access to the stream analyzer. Why? Because you need to understand the properties of the bulk solution. And that's what we do in this part of the software. The stream analyzer gives you everything related to the bulk solution. So if you have water, if you have oxygen, CO2, H2S, how that H2S, how that CO2 is going to dissolve. And then we transfer all of this knowledge, this bulk solution knowledge, to the corrosion analyzer, where we can actually do and calculate corrosion rates. And I will drill this a little bit more later in the course. And that's the reason why you will always see these two softwares together. You will also learn how to select the appropriate thermodynamic framework that we have available in the software. And the reason why is because you'll see that depending upon the needs, you will you can use different thermodynamic frameworks. But when you are working with Corrosion Analyzer, to date, we only use one framework, and that would be the AQ thermodynamic framework. That's the only one available to calculate corrosion rates. We are currently working to transition to what we call the MSc, and it will make more sense to you when I start talking about the properties of solutions and so on. Why is it important to transition to the MSc thermodynamic framework to calculate corrosion rates? Okay, so we will review general corrosion rate calculations. We will also understand how to interpret results for localized corrosion, to understand if you will have pitting corrosion, crevice corrosion, those type of localized corrosion. You will also learn how to interpret the pore bay diagrams, how to enter your own data, either if you have it in a molecular way or if you have it in water analysis. So sometimes produced waters, especially if you're doing oil and gas or if you're doing geothermal, you'll notice that they will give you a water analysis. And those water analyses come in ions. And the software has the ability to make possible that as an entry, calculate properties and then corrosion rates. And of course, we will learn how to interpret your corrosion rate results. The software has a lot of ways to show you the data, plots, tables, diagrams, and sometimes it can get a little bit overwhelming trying to understand where the data is and how to understand it and what it means. So I'm here to help you and guide you to understand what like an MVG means, right? Or what true species means, or apparent species means, things like that. You will see what I mean once we are working in the cases. Now, you should have received a manual I have put together, and those are the examples basically that we will be working on, the examples in the manual. You should have access to the software either through your company or through the virtual machine that Jim created for you. So make sure that you is up and running, either the software in your machine or the SkyTab remote desktop. And like Jim said, we're recording this session, so we will be able to share it with you. This is the agenda. Again, these are topics I came up with because I think that they are useful to understand how the software works, where to find information, highlight features. But again, down here is optional. For example, this topic here, and we can always cover some cases that are more relevant for you. If you're having technical issues, please let me know. I can help you. If you want to interrupt me anytime to ask questions, please do so. Don't worry about that. Just go ahead and unmute yourself and ask questions. And I don't know why I have this here again. Oh. So at the end of this class, then Jim, my colleague, he will be sending a survey to rate the course, and then you will be receiving a certificate of completion that you have taken the OLI Corrosion Analyzer class. And I already talked about a little bit about this, about the OLI Studio. The OLI Studio is a suite that has 3 different environments or 3 different add-ons. The Stream Analyzer, this one is very important when you're working with, to understand the properties of streams, the properties of a water and oil and gas analysis that you have, and you want to understand pH, conductivities, what happens if temperature changes, etc. All of these studies, you do it in the Stream Analyzer. The corrosion analyzer is, like I said before, once you have your bulk solution that is going to touch a metallic surface, Then you come to the corrosion analyzer and basically specify the corrosive conditions with the flow type of the fluid, the metal or the material, the metallic surface, etc. And the scale chem is a different add-on, more related when you are working in upstream oil and gas, is for predicting the scaling due to the mineral scaling, right? So if you have barite, calcite, and it's also, now I am using it a lot to do geothermal applications. If you're producing a fluid, very similar to what happens in oil and gas, but now with geothermal fluids. So it becomes really important when you want to calculate scale information. The Stream Analyzer software, I already talked about this, has 3 different thermodynamic frameworks. The AQ model was our first model that we created when this company was created. So it's our legacy model. But it has limitations. It has some limitations when it comes to concentrations of ions or salts, right? So if you increase the molality or the ionic strength of your solution, then it starts having some limitations right there. Also, if you go to, I don't remember the temperatures, but if you go above the critical temperatures, I think that it also starts having limitations. So to avoid those limitations, to overcome those limitations, then we created the MSc thermodynamic framework. That stands for mixed solvent electrolyte, where there is not a limit in concentration of salts, and you can go to higher temperatures and higher pressures. I think the limit is up to 350 degrees C and 4,000 atmospheres. Then we realized that the MSc model is not ideal when you're working at with supercritical fluids, with critical fluids. And so then we introduced this SRK, or the Soavi-Redlich-Kwong equation of states, to capture a smooth transition between, let's say, vapor to liquid phase, vapor-like to liquid-like phases. And this is mostly used in upstream oil and gas, and when we are working with autoclaves as well. So this is where we recommend the usage of this thermodynamic framework. And we will learn, like you will see, you will identify when to use which as we do examples in the software. For the corrosion analyzer, what do you get out of it? You get general corrosion, localized corrosion, polarization curves, 4-way diagrams. You can also understand the heat treatment effects and depletion profiles for the grain boundaries. And we also have a tool that is called extreme value statistics that works mostly for to determine the asset life of a material, of a metal, based on probability, basically. This doesn't really have a corrosion theory behind it. It's more probabilistic. If you're interested, let me know, and we can talk about this in the training as well. Okay, so let me talk about corrosion, the corrosion technology, the OLI, specifically how OLI has developed this corrosion model. So every time that you use it, you understand what type of calculations, what's going on, what the software is doing when it's giving you a corrosion rate. When we all know that for corrosion to happen, there are several factors that can influence corrosion damage. And the main one is the chemistry of the aqueous solution, right? So if you have chlorides, for example, the concentration of chlorides is going to affect the corrosion rates, or even the localized corrosion damage. The pressure could be, depending upon how high the pressure is, right, or what components you have, the pressure can play an important role on solubilities, etc., for components in the water. Temperature, for sure, we know that there are critical crevice temperatures, critical pitting temperatures. It is an important variable and it affects corrosion rates. The presence of known aqueous phases such as gases, acid gases, H2S, CO2, these components are very, well, they dissolve in water. And when they dissolve in water, they are going to make the water acidic. They are going to dissociate, create H+ in solution, etc. And that is going to have an impact on the metallic surface as well. Flow velocity is another variable that is very important to consider when we are studying corrosion rates. It's different if you have a static condition, or is and the corrosion rate will be higher if you have a flowing condition, right? And all of that has to be with the transport properties. It will be influencing transport properties, which are important again for corrosion rates. And finally, the composition of the metal alloy. We know that the corrosion rate is not the same for a carbon steel, and it's not going to compare to the corrosion rate of a stainless steel, because you will have different compositions. You will have chromium, molybdenum, and that are going to cause passive layers, etc. And that's going to reduce the corrosion rates. So what the software does is that it takes into account all of these different variables in the corrosion model. Okay, so the corrosion, the chemical equilibrium, and the thermophysical properties is taken care for by the stream analyzer for all the bulk solution, but all the metal solution interface reactions that happen are taken care by the electrochemical module, or the electrochemical module in this OLI corrosion model. So like I was saying before, the thermophysical properties, okay, that's all done here, speciation, bulk solution, transport properties, etc. But this is what's new, the electrochemical module. We simulate partial oxidation and reduction processes that happen on the surface of the metal. We also simulate passivity. We can reproduce active to passive transition and the effect of solution species on passivity. So there are some species, molybdates, for example, is one, or chromates, that will cause passivity, and we will take into account those in the model. We also have a model in the electrochemical module. We have the repassivation model, which help us understand if we will have localized corrosion or not. So we put all of this together, and I'll show you in a plot how we do this. And we can calculate corrosion rates, a theoretical corrosion rate. And then what we do is that we validate our model using experimental corrosion rates. If we are far away from those, if the theoretical corrosion rates are far away from experimental corrosion rates, then we calibrate our model using that experimental data. Okay, so we go to the literature, find corrosion rates, let's say, of carbon steel and CO2, do our predictions, and if we are far off, then we start tuning the model, changing some parameters in the corrosion model until we have we calibrate the model based on the experimental data that we find in the literature. So this is what I was saying about how we calculate the corrosion rate. We use the mixed potential theory. We put all the anodic processes together, all the cathodic processes together, and those anodic processes include the dissolution or the active metal dissolution, active-passive transition, passive dissolution. The cathodic processes are the reduction of all of these different species on the metallic surface, and we also take into account the diffusion-limited processes. So when the anodic and cathodic processes have the same current, total current, would be this value here. That's what we call the corrosion potential. And I know this sounds a little bit probably esoteric at the moment, but this will make sense later in the software when we are using the software. This corrosion potential then is the theoretical value that we use or we calculate, and we back calculated to obtain the corrosion rate. This is the mixed potential theory put in practice or visually what's going on. This is the activation control or the anodic reactions. We are using the Butler-Volmar equation to calculate this part of the polarization curve. We are also using for the limiting current density the diffusion control. We have the active to passive transition to, well, actually this is the surface coverage, the fraction surface coverage model that we use to reproduce the passivity. Then we put them all together and create a polarization curve. And whenever the active, this blue curve, the anodic curve, touches this cathodic curve, the turquoise here, this would be the corrosion potential. Again, I'm just talking about this, but we will learn more in detail how we can interpret this. But I just want to show you that we have studied this phenomena and that you can always go back. I have put here the one of the papers where we describe very well how this mixed potential theory works and how we calculate those corrosion rate values. Okay, I promise this is all the theory that you're going to see for today. I just like to show why or how we do these calculations. Now, these are some of the applications that can be simulated using OLI. Probably I should add even more here. We are able now to do geothermal, for example, because I have been working in some cases for geothermal, and we could add some other applications in here as well. But mostly we focus on the CO2 corrosion, caustic corrosion. We do acid, sour water corrosion. We have some organic acids, so we also do organic acid corrosion. We do cooling water corrosion, sulfuric acid corrosion, and HF corrosion as well. So these are some of the examples that of some of the applications that our customers commonly use the software for to get those type of values. Now, it is also important to know, okay, so you can calculate corrosion rates, but what are the surfaces or alloys or metals that you have in the database that we can calculate corrosion rates? And this is a list of 30 different alloys. I think it's 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 29. So these are 29 different alloys that we have as part of our database. So you'll see we have carbon steels. We have for oil and gas, this 13 chromium stainless steel, super 13 chrome, 15 chrome, 17 chrome, duplex stainless steels. We have the stainless steel 304 and 316. Some nickel alloys here, Inconels, Hastelloys, aluminum alloys, more nickel alloys around here, copper nickel alloys as well. These are part of the database, and we have studied all of those alloys. And what we do, like I was saying, is we go to the literature. This is for carbon steel. So we go to the literature, find the corrosion rates, make sure how the software is, how well the software is doing, the predictions, and if not, then we just calibrate the model, and you'll see The data points here are the experimental data, and the solid lines is the predictions made by the corrosion model. Okay, so all of these are validation plots. We have them for all the different alloys that I am showing here. All of those alloys have some sort of a validation plot. This is a validation plot I like to show because it's relevant, especially for oil and gas. We also include in the corrosion rate the effects of corrosion scales, iron carbonate and iron sulfide. This is in carbon steel, and you'll see the data points in the literature are these squares here, and the solid line is the corrosion rate prediction made by the OLI model. So you'll see that the corrosion rate increases as the temperature increases here. And then you start seeing a decrease in the corrosion rate because you're forming an iron carbonate layer on your surface, and then you start seeing that decrease in the corrosion rate. Similar behavior you'll see for H2S environments, iron sulfide, so you have a very high corrosion rate, you start forming your iron sulfide layer, you see a decrease in the corrosion rate, then as you increase the partial pressure, then you'll see an increase in the corrosion rate. Yes, Mariana, you have a question?
Yes, thank you, Diana. My question would be if we have also this type of correction, this type of validation for high temperatures, because as far as I know, the type of scaling that is forming at 80, 70 Celsius degrees, it will be not the same that the ones that you form at higher temperatures. So I wanted to know if this factor that you are using here to model this is also available at higher temperatures.
What is a high temperature for you? Above what?
180, 200 Celsius.
180 and 200 Celsius. No, we don't include any other corrosion scale. We have validated only the iron carbonate, iron sulfide. I'm not aware of any other iron scale or iron corrosion scale at higher temperatures that we have included in the model. So it will be interested for me. I will be interested to know if you have a paper where it shows the layer that you are expecting to form, and see if we can maybe model it or include it in the model if it's becoming of relevant importance in the industry.
I will look for one. I don't have any specific thing, but what I was thinking was in the Courbet diagram, that maybe that will show you that the type of products that could be formed are not the same that are formed at lower temperature.
Right, no, and that makes sense. But I know because I think I went to the CTO to ask this question also, and no, it's purely kinetics at those temperatures, right? Purely kinetic predictions that we're doing, and we are not including any other type of layer above those temperatures. But again,
thank you.
Yeah, but again, if they are relevant and we need to include them, we are all ears because we always want to improve the corrosion predictions. Sure.
Thank you.
Sure, no problem. Okay, so those are the validation plots we have for different alloys, etc., etc. You get the idea. The main point is, okay, if you are working, let's say, with super 15 chrome stainless steel and you want to know if we are doing a good job on the corrosion rate predictions, you can always ask for those validation plots And like I was just saying, if you feel you think that something is missing, the predictions are off, don't hesitate to tell us, because we need to know, right? Because if we can make those corrections or those improvements, we will be happy to prioritize them and make sure that we are doing a good job on taking into account those the right predictions, or at least to be aware that there is new data out there and that we can improve the model predictions.